Right now, there is an invisible wall surrounding our entire universe. Scientists call it the Observable Horizon. It sits exactly 46 billion light-years away in every direction. And for decades we treated it as the edge of everything, the end of the map. But something is wrong with that assumption. 3 independent lines of evidence, from 3 different instruments, 3 different research teams, 3 different corners of the sky, are all pointing at the same conclusion. The cosmos we can see is not the cosmos that exists. And what lies beyond our horizon may have already left its mark on everything we can observe. If you want to understand what the most powerful telescope ever built just found at the edge of the universe, and why it is forcing physicists to consider ideas they once called outrageous, stay with me, because the next 12 minutes will change how you think about the sky above you. To understand what's happening at the edge of our universe, you first need to understand what the observable horizon actually is. It is not a physical wall. There is no barrier, no fence, no change in the laws of physics at 46 billion light-years. It is a horizon of time. The universe is 13.8 billion years old. That means the oldest light we can ever receive has been traveling for 13.8 billion years. And because the universe has been expanding the entire time that light was traveling, the source of that light is now 46 billion light-years away. Beyond that distance, light has not had enough time to reach us. Not because nothing is there, but because the universe is younger than the journey would take. Think of it this way. You are standing in the center of an enormous expanding room. The room is filling with sound from every direction. But the room started expanding the moment the sound began. Some of that sound has not reached you yet. That doesn't mean the room ends where your hearing ends. The room is much larger than what you can hear. Our observable universe is the bubble of light that has had time to reach us. The actual universe, if standard cosmological models are correct, is at minimum 250 times larger in volume. Some estimates put it far beyond that. We're not looking at the universe, we're looking at our neighborhood. And here is where it gets disturbing. If the universe extends far beyond what we can see, then events that happened outside our horizon, before our Big Bang, or in regions we can never observe directly, could still have influenced the structure of our cosmic neighborhood. Like ripples from a stone thrown just over the horizon, you cannot see where the stone landed, but you can feel the waves. Now here is the first piece of evidence that something is beyond our horizon. In 2004, astronomers analyzing the cosmic microwave background, the faint afterglow of the Big Bang, still detectable in every direction of the sky today, found something that should not be there. A void. A region of the CMB roughly 3 billion light-years across that is significantly colder than everything around it. Colder than our models predict, colder than random chance should produce. It has been confirmed by the WMAP satellite, the Planck satellite, and multiple independent analyses. It is not an instrument error. It is not noise, it is real. Scientists call it the CMB Cold Spot, and for 2 decades it has sat in the data like a bruise, with no known cause. The standard explanation, that it's just a statistical fluctuation, has a probability of less than 2%, meaning if you ran the Big Bang 100 times under our current model, you would expect this void to appear roughly twice. It is possible, but it is not comfortable. Then, in 2006, a physicist named Dr. Laura Mersini Houghton at the University of North Carolina proposed something radical. She was working from a model called the landscape multiverse, the idea that our universe is one of an enormous number of possible universes, all emerging from the same underlying quantum landscape, like bubbles forming in foam, each one a different cosmic configuration. And in this model, she made a specific prediction. If neighboring universes existed during our Big Bang, their gravitational influence would have left detectable marks in the CMB. The cold spot should be one of them. She predicted its approximate location and size before the Planck satellite confirmed those measurements. That is not a metaphor. That is not a coincidence. That is a prediction that matched the data. Some physicists are now calling the cold spot the supervisor's imprint, the gravitational shadow of a neighboring universe pressed against ours at the moment of our birth, leaving a permanent mark in the oldest light we can observe. We may be looking at the scar from a cosmic collision that predates our Big Bang. The cold spot is not the only anomaly. According to the Big Bang model, the universe at the largest scales should be isotropic. That is the technical term for the same in every direction. No preferred axis, no up or down, no left or right. The universe should not know which way it is pointing. And yet, when we map the temperature fluctuations of the CMB across the full sky, we find something that should be impossible. The northern hemisphere of the cosmos is statistically different from the southern hemisphere. The distribution of matter, the temperature variations, the arrangement of the largest structures, they are not uniform. They are aligned. They point along a preferred axis that runs through our observable universe like a spine. Cosmologists have, with a mixture of frustration and dark humor, named it the axis of evil. Because it violates one of the foundational assumptions of modern cosmology, if the universe has a preferred direction, it means something. Something in the initial conditions of space and time broke the symmetry. One explanation: inflation, the period of exponential expansion just after the Big Bang, was not perfectly uniform. Different regions expanded at slightly different rates, creating the asymmetry we now observe. A more uncomfortable explanation: the asymmetry is a boundary effect. The edge of our observable universe is not the edge of everything. And the structure beyond our horizon, the geometry of what we cannot see, is pulling on what we can. An axis implies a direction, and direction implies something on the other side of it. Something our universe is oriented toward. Something our current instruments cannot reach. If the cold spot is a bruise, the axis of evil is a lean. Our universe is not sitting still in a symmetric void. It is tilted. And that tilt is pointing somewhere. If a bruise and a tilt are not enough to convince you that something is beyond our horizon, what James Webb found in 2023 should be. Modern cosmology has a rule about how large a structure can be. It comes from the speed of gravity and the age of the universe. Gravity has been pulling matter together since the Big Bang, but the universe is only 13.8 billion years old. There is a hard limit on how much matter gravity could have organized in that time. That limit is approximately 1.2 billion light-years. Structures larger than that simply should not exist. There has not been enough time for them to form. In 2021, astronomers announced the discovery of the Giant Arc. It is a vast structure of galaxies, galaxy clusters and gas that forms a curved arrangement in the sky. It spans 3.3 billion light-years, nearly 3 times the theoretical maximum. Then came the Hercules Corona Borealis Great Wall. Discovered in 2013 and confirmed by subsequent observations, it measures over 10 billion light-years across, almost the width of the entire observable universe. Then, the South Pole Wall, the Sloan Great Wall, the Boots Void, a sphere of near-empty space over 300 million light-years across that contains almost no galaxies where there should be thousands. The pattern is consistent. At the largest scales, the universe is not behaving the way our models predict. It is more structured, more asymmetric, and more extreme than the Big Bang alone can explain. When the James Webb Space Telescope pointed at the deep field, a tiny patch of sky near the Big Dipper, it detected galaxies from the first 500 million years of cosmic history that were already the size of the Milky Way. Fully formed, mature, organized galaxies that should have taken billions more years to build. Astronomers called them the universe breakers, because that is what they do. They do not fit. Not in our current models, not in any simple modification of those models. They require either a complete rethinking of how galaxies form, or they require something that was already in place before the standard Big Bang narrative begins. Something that seeded the universe with structure before we thought structure was possible. Which brings us to the man who may have the most coherent explanation for all of this, Sir Roger Penrose. Penrose is a British mathematician and physicist. He won the Nobel Prize in Physics in 2020 for his work proving that black holes are a direct consequence of Einstein's general relativity. He is not a fringe theorist, he is one of the most rigorous mathematical physicists alive. And he believes our Big Bang was not a beginning. His theory is called conformal cyclic cosmology. The central idea is this: the universe does not start and stop, it cycles. When our universe reaches its final state, a cold, dark, near-empty void where all matter has decayed and all black holes have evaporated through Hawking radiation, something happens at the mathematical boundary of that void. In the language of conformal geometry, an infinite future can be mathematically rescaled to look like a finite beginning. The end of one universe and the beginning of the next become geometrically identical. In simpler terms, the far future of a dying universe and the moment of a new Big Bang are the same event seen from different sides of an infinite boundary. Our Big Bang, in this model, was not creation from nothing. It was the death of something else. Now here is where the theory makes testable predictions. Penrose argues that as black holes evaporate in the previous universe, a process that takes longer than the current age of our universe, but eventually completes, the final burst of Hawking radiation gets carried forward into the next cycle. In our universe, those photons from the previous cycles evaporating black holes would show up as concentric rings in the CMB, circular patterns of slightly different temperature, fossil imprints of the previous universe's largest black holes. Penrose and his colleague Vahe Ghazadian searched for these rings in data from the WMAP and Planck satellites. They found them, not just in one dataset, in both, independently confirmed. The circles appear at the statistical significance Penrose predicted at the angular sizes consistent with supermassive black hole evaporation timescales. He calls them Hawking points. The scientific community remains divided. Some researchers have argued the circles could be statistical artifacts, patterns that emerge from random data if you look hard enough. Others have argued the methodology is sound and the signal is real. Penrose is not discouraged. He points out the black holes themselves were once considered mathematical curiosities that could not exist in reality. Now they are observed directly. The history of physics is full of predictions that seemed absurd until the instruments caught up with the mathematics. If Hawking points are real, then the CMB, the oldest light we can observe, contains the fingerprints of a universe that ended before ours began. We are not just looking at the past, we are looking at evidence of what came before the past. We built our entire understanding of the cosmos on one assumption, that the Big Bang was the beginning, that the observable universe is the universe, that the edge of what we can see is the edge of what exists. Three independent anomalies, a bruise in the CMB, a preferred axis across the sky, and structures too large to have formed in the time available, are all pointing at the same unsettling possibility. That assumption is wrong. And science, when it is working the way it should, does not panic when an assumption fails. It updates. So the next time you step outside at night and look up, remember what you are actually looking at. You are looking at a horizon, not an edge. And somewhere beyond that horizon, something that was not born in our Big Bang may have left its fingerprints on everything you can see. We are 13.8 billion years into a story that may not have a first page. If a universe without a beginning sounds impossible, subscribe, because the next video asks something even stranger, whether the universe we live in might be a simulation running inside another one. The evidence is more serious than you think.